Hello, everyone. Today I am excited to present our work on multimodal label relevance ranking via reinforcement learning. We will start with the motivation, then introduce the problem setting and challenges. Next, I will present our proposed method and dataset. Finally, we will review the experimental results and summarize our main contributions. Traditional multi-label recognition methods focus on label confidence, which is the probability that a label is correct for a given instance. However, this overlooks the importance of label relevance, which measures how significant a label is to the context. For instance, in a movie scene, the label car might be less relevant than car chase. By focusing on label relevance, our method better aligns with human preferences, emphasizing important labels over less significant ones. Our goal is to rank labels based on their relevance to multimodal inputs like video clips and text descriptions. Each video clip consists of multiple frames and a set of recognized labels. We aim to learn a ranking function to order these labels. We use NDC metric to evaluate our ranking performance. Our method, LR2PPO, consists of 3 stages. Stage 1. Establish a base model using source domain data. Stage 2. Train a reward model with preference data. Stage 3. Enhance performance by integrating the critic model with the actor and reward models. In Stage 1, we train the base model using manually annotated data with categories like high, medium, and low relevance. We extract visual and textual features and fuse them to predict relevance scores. In Stage 2, the reward model is trained on the target domain using a few annotated label pairs. This model assigns rewards to partial order relationships, aligning with human preferences. Stage 3 refines the framework by redefining the state and policy loss. The state is represented by the order of a label pair at each time step, and the action is the policy network prediction of the relevance score, resulting in a new label order. Unlike typical PPO tasks, label relevance ranking requires considering the entire probability distribution of label orders. To achieve this, we define a partial order function to distinguish between correct and incorrect label orders, adjusting the advantage estimate accordingly. We introduce partial order ratio to further refine policy updates. This ratio, which depends on the sign of the estimated advantage at each time step and uses a small negative threshold, helps stabilize training. By penalizing incorrect orderings, the partial order ratio guides the model to rank labels correctly. This stage integrates the actor and critic models, iteratively updating them to enhance overall performance. The core algorithm initializes the state with the original label order. The policy network predicts relevance scores, resulting in a new label order. The reward model evaluates this order, and we iteratively update the actor and critic models. This process adapts the model to partial order relations, improving label relevance ranking. We introduce LR-MoveInit, a dataset designed for multimodal label relevance ranking. It includes annotated samples with relevance categories and partial order annotations. This dataset features various multimodal labels, providing a comprehensive evaluation of our model. LR-MoveInit contains 101627 labels for 2551 clips, with a total of 15234 distinct label classes. We extract frames and labels using the RAM and Llama 2 models, then manually filter and modify them to ensure accuracy. This dataset diversity helps evaluate our model performance effectively. Our experimental results show that LR2PPO significantly outperforms previous methods for label relevance ranking. We achieve higher NDC scores, demonstrating our approach effectiveness in accurately ranking labels based on their relevance. We also test LR2PPO on traditional LTR datasets. Our method outperforms previous LTR methods, showing its generalizability and robustness across different scenarios. We find that the original PPO ratio leads to training collapse, whereas our partial order ratio stabilizes training and improves performance. Additionally, a small negative threshold further enhances stability and NDC scores, proving our design modifications are crucial. We explore the impact of varying annotation proportions in the target domain. Even with limited annotations, our reward model and framework achieve high performance. Using around 10% annotations balances effort and performance, showing our method efficiency. We compare LR2PPO with other ranking methods like CLIP and PRM. Our method consistently ranks high relevance labels at the top and low relevance labels at the bottom, aligning better with human preferences and providing more valuable insights. To summarize, our work: 1. Highlights the importance of label relevance and proposes a novel ranking approach. 2. Designs a paradigm for transferring ranking ability from the source to the target domain. 3. Introduces LR-MoveInit for comprehensive evaluation, demonstrating our method effectiveness. Thank you for listening. If you have any questions, please feel free to ask. For more details, you can check our paper on ECCV or visit our GitHub repository. Thank you.